This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
Today we have Maneesh Agrawala, who I'm pleased to say is one of our own students. He graduated from the department here a couple of years ago, working in cognitive issues in graphics and interaction, which is still the general area he's in. Did a very well-known program called Line Drive, which you're going to talk about it.
I'm not going to talk.
He's not going to talk about it. So how do you get a computer to draw maps the way that somebody would draw a map for you on a napkin, which pulls out the cognitively relevant features and leaves out or distorts the stuff that's irrelevant? And it was actually a very successful thing that was been used. It's online. It's available. He was at the University of Washington for a while, and then since I see a bunch of students here for recruitment weekend, I'm afraid I have to say this, he went to the dark side. There's this school up north, somewhat close to here, and for some reason he decided that was a good place. Actually, he's really rejuvenating, I think, the HCI Group of Berkeley. I think it's great to have him there. And we like having him in the area, even if he's on the other side. So today we have Maneesh Agrawala.
Thanks, Terry. It is nice to be back down here in Palo Alto. I spent a number of years here. I was an undergrad as well as a graduate student here, so this really feels like home. Although I forgot where the bathroom was located in this building. So as Terry said, I've been working for a number of years in trying to understand how visual displays, visualizations, communicate information to people. And this is really a problem where we need to study the computer and the algorithms, but just as much we need to study the people and how people understand the visual displays that they're given. And so a lot of the work that I've done has focused on trying to understand how images communicate information. What I want to talk about today is some work that I've been doing over the last couple of years on creating interactive diagrams of complex three-dimensional objects. And this really brings together my interest in visualization on one side, as well as in illustration on the other side, in computer graphics and HCI. So let me start with a motivating example. I've shown these examples quite a lot because I think they're really, really inspiring. These are two structural illustrations. The one on the left is from Leonardo da Vinci, and it shows the principal organs and vasculature of the human body. And what's really interesting about this illustration is that Da Vinci made a number of design choices to help emphasize the important aspects in this image. Okay? He carefully chose where to cut the body to expose its internal structure. He chose to show this rough outline of the bodies to give you a little bit of context so you could see where the organs are located. He used shading very, very effectively to highlight the important organs. He also exaggerated the size of important organs. And perhaps most importantly, he removed extraneous detail, right? Things that would be distracting are gone from this diagram. Over on the right is an image that was created by Cassidy Curtis. And it shows the immersion of a torus in 3 space. It's this geometric object. And again, Cassidy made a number of design decisions, very carefully chosen to expose the important aspects of the structure. He carefully chose where to cut this thing apart. He ensures that you can see important geometric and topological features where the surface self-intersects. He uses shading to help emphasize that. He uses placement of the objects to help you understand how the thing fits back together. And so this is a really, really nice example of a kind of structural illustration of a complex 3D object. And in fact, I should tell a little story. It turns out that Cassidy created this when he was I think he was an undergraduate at Brown University. He created it for one of his math homeworks, and Tom Banchoff, his professor, said it was the best math homework he had ever gotten. And recently this thing was on Dig. You might have seen it. It got lots of digs. So this thing is sort of a well-known illustration. So these are examples of the kinds of things that I'd like to be able to create. I'd like to provide tools to make it easy to create these kinds of structural illustrations. Now, the nice thing is that with today's technologies, we have the data, the internal structures of very complicated objects. We have human anatomy. So the Visible Human Project gives us volumetric data, all of the voxels inside the human, and we can see the organs, and we have the complete internal structure. Similarly, people have spent time geometrically modeling all of the organs in the human body, the vasculature, and so on. So the data is becoming available, and it's not just for human bodies. For mechanical objects, we have nice CAD models of these things. For architectural buildings, again, we have very nice models that contain a lot of the internal structure. The challenge, of course, is how to visualize this structure, right? And these are nice images in a sense because they reveal the complexity of the human body. But what's difficult to see in these illustrations is the spatial relationships between the different parts. Okay? So when we just have a slice through the body, through this volumetric object, we get a sense for some of the organs, but it's hard to see how the different organs relate to one another spatially. We can't see the layering relationships between the different organs. We can't see any of the organs that were in front of the organs that are depicted here. Okay? And similarly, in this example, they've used transparency so that you can see at least inside of the skin. But again, it's very difficult to see the layering relationships between all the different parts. You know that there are different parts in layering that layer with one another, but beyond one or two levels of transparency, it's hard to distinguish between the parts and really get a sense for what's going on structurally speaking. Okay? And let's just compare that to a hand-designed illustration. Okay? This is a medical illustration from Frank Netter. He's one of these master medical illustrators. And if you take anatomy classes in the med school, for example, you often have to buy his book, which contains hundreds of pages of these kinds of illustrations. What's great about these things is that they're designed to, again, reveal the spatial relationships between the parts. You can really see the layering of the different organs. Important parts are highlighted. He's carefully chosen which parts to remove. And this is done in a much better way than these sort of simple computer-generated renderings. And so what we want to do is build tools that push in the direction of being able to create these kinds of illustrations. And the reason we want to build tools to help is that designing these kinds of illustration currently requires a great deal of skill. So you need to be a master medical illustrator. And even the masters require quite a lot of time. So there's no way, if I generate a new data set, a new building or a mechanical object, or if I take a scan of my body, there's no way that I can have a master illustrator create an illustration that's customized to me. And so what we really need are computers to help us out a little bit and help us produce illustrations that are as effective as the hand-designed one. And we're going to move in that direction. I can't say we've solved the problem, but hopefully we're moving a little closer. The other thing that the computer brings is interaction. Okay? So with 3D objects, interaction is really critical to help understand the 3D spatial relationships. Here's an example of a kind of interaction that was done by a group in Germany on the Voxelman 3D. And here they're just sliding a plane, a cutting plane, through the object, through the visible human data set. And it starts to reveal the internal structure. But what's nice is this direct manipulation of the cutting plane gives you a much better sense for the 3D relationships, right? And that's been shown again and again in the HCI community, that this kind of direct manipulation in 3D is very, very important. So we want to design the right kinds of interactions for these 3D diagrams. Over the last few years, I've been taking a general sort of three-stage approach to creating these kinds of visualizations. The first step is to really think about the appropriate design principles for the visualization or the illustration that we're trying to create. And we do this typically in three ways. One is we look at the best examples of visualizations within a particular domain. So we'll start by looking at Da Vinci, Netter, Cassidy Curtis. We'll look at really well-designed examples and try to find commonalities between them. And this gives us a kind of indication of the techniques that really well-designed visualizations use. Another approach is to look at previous research in visual perception and in cognition. And that research often has, people have studied visualizations previously. We want to look at that research and apply the results of that research to our work. So this was what we did in particular for the work on line drive, the map drawing system that Terry alluded to at the beginning. It turns out a lot of people had studied cartography and the way people used maps, and we could apply that research directly to our problem. And similarly, we try to do the same kind of thing with these kinds of visualizations. Finally, the last approach is to conduct our own user studies. We'll go and ask users, the users of these kinds of visualizations, to create examples by hand. So we'll ask medical students to go and create medical illustrations. And they might not have the best drawing skills, but they often will, there will often be commonalities between the drawings that these medical students create, and we can learn from those commonalities. We can start to pick out what might be important to include in these kinds of illustrations. So that's the first step. We identify these design principles, and then we become computer scientists again. We go and instantiate these in algorithmic tools for creating these visualizations. And finally, when things are going well, we evaluate the resulting visualizations and we try to decide if they are indeed effective at communicating the information that we wanted to communicate. So that's the basic approach. And what I want to show you today are three examples of projects in which we've applied this basic approach. One in the domain of interactive diagrams of architectural buildings, one in the domain of mechanical objects, exploded views of mechanical objects, and the final one is on creating cutaway diagrams of anatomy as well as mechanical objects. So let's start with the first project. And this was done as I was leaving Stanford. So in fact, some of you might know some of the people on this project. This was done in conjunction with Chris Niederauer and Mike Houston, who I believe is still here as a PhD student, as well as Greg Humphreys, who's a professor over at UVA now. And the idea here was that there are lots and lots of 3D environments, like buildings, but and photographs of these environments are very, very nice. They show me what the building looks like from the outside. But one of the things that I'm very interested in is seeing the internal structure. I'd like to be able to take Soda Hall, this is where I work at Berkeley now, and I'd like to be able to see where all the offices are. I'd like to be able to make maps that show me how to get from one office to another. This was especially important to me when I first started about a year ago at Berkeley. I had no idea how to get around the building, and I didn't have a good way of visualizing the paths that I needed to take. So what I'd really like is to be able to see inside of this thing. And so the first thing to do is think about the appropriate design principles. We can learn from designs that designers have created, that architects and museum guide designers create to try and understand what is important about internal structural diagrams of buildings. And so one of the things that they often do is they will create these kinds of exploded views. They'll take off the outer walls, right, because those walls are occluding the internal structure, and they'll pull apart the building like an exploded view and allow you to see inside from this third-person axonometric perspective. It turns out that in cognitive psychology, Sylvie Fontaine has studied these kinds of diagrams a little bit. She studied different perspectives on these kinds of maps of 3D environments. And what she found is that external oblique perspective views are better than egocentric views, or views where views from the perspective of a person inside the building, like you would get with a walkthrough. And she also found that a single integrated 3D view is better than multiple 2D floor plans. So if you just showed, another way to create these kinds of maps would be to show each floor separately, but that's not quite as good as having this kind of exploded view. Yeah.
So, I mean, I can see that if you're trying to go from this building to this building, that's great. But if I actually wanted to know, the office is on the second floor of the east building, it seems like a single 2D floor plan would be easy.
Yeah, so the floor plan is not so visible here, but there is the floor plan is sort of shown in this kind of oblique perspective. So so you do get the floor plan, but the main thing that Fontaine studied was floor plans that are integrated together into a single diagram versus floor plans that are sort of separate from one another, a series of small multiples. So those are the design principles, and the next step is to create an exploded view diagram of 3D geometry. So here's a nice 3D model of Soda Hall, and we can basically do a kind of geometric analysis to figure out where the different floors are located, and then split apart this building and allow users to interact and look inside and really see the structure, the internal structure of this thing. Okay, so that's the basic algorithm. It's a very, very simple algorithm to find the basically downward-facing ceiling polygons, insert a cutting plane just below those, and pull the thing apart. But what's neat about this system is that we use this trick where we intercept the OpenGL graphics stream and modify that stream directly. What that allows us to do is apply this to existing applications like this first-person game, and we get a kind of spectator mode where we can see the different characters running around and interacting with each other. Okay? So all we did here was we took, we're capturing the OpenGL stream, we're modifying it, and re-rendering it in this way. We're replacing the OpenGL library with our own version of that library. And so this application didn't need to be modified at all. We just link it against our own library. And that provides this view where you can see a lot more of the interactions taking place, and you can see the structure of the building. Okay? So, that's the first step. Yeah.
I'm sorry, so what, the original stream, what would I have seen? Just like one person running around?
Yeah. So typically in these first-person shooter games, as you might have seen, you see one person, you're either a character yourself running around and seeing it from your perspective, as if you're walking through the building, or sometimes they have spectator modes where you're looking from over the shoulder of one of the characters.
But then how do you extract all the surroundings if you see in the stream just that egocentric?
The stream contains more. You can set it in a mode where it contains all of the geometry. That's right. We turn off the culling. We have to do that. Yeah, good point. So that's the way the basic system works, and it's and it's useful for seeing individual games. But where eventually we would like to go with this is to really visualize what's going on in the environment, right? And how the different characters interact with each other, as well as the features of the environment. And so here's a little mock-up of the kind of thing you could imagine doing. You could put in labels for the different characters, see where they are. You could even see when they're off screen, which is kind of nice. You know that something's going on down here, but you don't know exactly where this character is. And you can see the paths that they've taken. And so this would be, I think, a nice way to bring spectators more into these kinds of games and provide a view where they can really interpret what's going on. Another thing that I'd love to be able to do is visualize real-world environments. This is a library in Seattle. It's a neat building from the outside, but it's really neat from the inside. There's a big ramp that runs all the way through the library. There are bookshelves on both sides of the ramp. It's a very cool space, and you don't get that from just the external view. It would be nice to, again, split this apart like an exploded view, as is done by hand here, and really see what's going on inside. And then you could imagine tracking various things, like, maybe you could track all of the books in the library, the positions of all of the books, and then get a sense for the flow of the books through this 3D space. Or maybe you track the people and see how the people interact in this space. What are the places where people tend to congregate? What are the spaces that aren't working very well? So that's a future direction here. It requires tracking. It's not exactly clear how you would do that, but I think it would be very interesting to visualize that kind of information. All right, any thoughts or questions about that aspect?
Simple algorithm work. You have the ramp.
Mm-hmm.
I mean, it seems like that. Looking for the polygons.
Yeah. So we'd have to do something more intelligent, certainly, to handle those kinds of ramps. And maybe you could find large polygons that are, roughly horizontal. I don't know.
Do you have, I don't know what you call it, augmented, where you can say, use your algorithm, but here, do this?
Yeah. Not in this case. But in the next project that I'll show you, we have a lot of that. Because it's often nice to be able to bring in input from an author seamlessly into your system. So anything else? Okay, I'll then go on to this next project. So that first project was really about creating exploded views of 3D architectural buildings. And as I was working on that project, I got interested in looking at exploded view diagrams. And it turns out that there are quite a few exploded view diagrams or images in the world. You see them all the time in things like textbooks, in car repair manuals. Here's one from, this is a master cylinder of a car. This is from a car repair manual. They're used all over the place. And I think one of the reasons that they're used is to give people a real sense for 3D structure, right? They show you each one of the individual parts, and they give you a sense for how the parts fit back together. You can mentally sort of figure out how the parts will fit into one another. You can mentally reassemble it. And that's really nice, but most of these diagrams are also static, right? And because they're static, they need to contain a lot of information. They can be cluttered with extraneous information that you don't really care about. So if I'm interested in this portion of the master cylinder, I might not care about the push rod and the dust boot, and maybe that shouldn't be visible in the diagram. So there can be clutter. That's one problem. And the other problem is that the spatial relationships can be a little bit ambiguous. So although these kinds of diagrams are designed to facilitate this mental reassembly, it can still be difficult to do that. right? You have to mentally animate it. And so one of the things I thought was, well, wouldn't it be nice if you could turn this into an interactive diagram where you could press a button, the whole thing expands or collapses in that case, and then you can directly manipulate it. You can pull apart the objects and really get a sense for how they interact with one another, how they fit into one another, and the spatial relationships between them. And so this is a project on taking these static diagrams, these bitmaps, and turning it into these interactive diagrams. So first, the design principles. As we saw, the direct manipulation can help really clarify how the parts fit into one another. And the animated transitions allow you to, well, you bypass the whole mental reassembly. You're showing it directly how these things fit. And then the other thing is that you can reduce visual clutter, right? You can interactively filter and just expose the parts of the diagram that you're most interested in. And finally, you can highlight the things that you're interested in. So if I drag on a particular part, that part can highlight, or maybe that set of parts that it's involved with can highlight. And so the two things here are clarifying spatial relationships and reducing visual clutter. So we've built a pipeline, an authoring pipeline, to help take these bitmaps and convert them into these interactive diagrams. So it's not that you can just feed a bitmap into our system and out pops this interactive diagram. There is a little bit of authoring work involved. And the key idea in this authoring system is to provide a set of tools that make it easy to go from the bitmap to the interactive system. And the authoring pipeline is divided into 5 stages. The input, again, is an image. And then we go through these 5 stages, which I'll show you in a little more detail, to produce the final interactive diagram.
You try to fill in the part that was included?
We don't fill in the part that was included. And what we assume is that the input diagram is in its fully exploded state. It is actually, well, in the end, we're only going to allow it to explode up to this point. But for the purposes of showing you how the system works, I've separated them a little bit more.
You're never going to unocclude more than the artist did.
Yeah. And that's a bit of a problem. There are techniques to fill holes that you could imagine using to handle the cases where you disocclude parts. So here's the first step. The first stage in the system is segmentation. So we have this bitmap. We need to separate the parts from one another. And so what we use, we've built intelligent scissors, or this is equivalent really to the magic lasso in Photoshop, where you just roughly trace around the outside. The boundary snaps to the object, and as soon as you've completed the contour, we can separate out this part. Okay. So the first step is this segmentation, and we do that for all of the parts in this object. Now, the second step is to indicate the explosion direction for sets of parts. In this case, all the parts are really exploding upwards, and so we have sort of one stack of parts, okay, one explosion axis. And so the user draws the explosion axis, and we require the user to draw the explosion axis starting at the part that's furthest away from the viewer in the direction of the part that's closest to the viewer. Okay, so oops. So here's how it works. The user just draws a rough explosion axis. The system then figures out a line that best fits the centers of the parts, and that gives us a stacking direction. Now the parts are constrained so that they can only move along this explosion axis. Okay, so now we're getting closer to this interactive diagram. The one thing that you probably noticed there is that the occlusion relationships are not correct. This part here is supposed to fit inside this bottom part. And when we run the video, if we play that again, you'll see that the bottom part is not fitting inside the way it's supposed to.
Do you have 3D information, or is it really just what's there?
It's just what's there. There's no 3D here. But we're starting to get some information that's going to help us, right? So when the person drew that stacking direction, that told us, you know, which direction is further away from the viewer and which direction is closer to the viewer. So we're going to start using that a little bit. Here's the next stage. We need to solve this problem of one part fitting inside another part. And so what we have here is a step we call fragmentation. The issue here is that we need to take this bottom part and split it into two pieces. We need to figure out the part that's in front, which is this bottom part here, and we need to figure out the parts that's in back. And again, because we don't have the 3D information, we need a little more help from the user, from the author. And so the way this works is that the author draws a curve on the top rim of the object, right? The place where this top part has to fit inside, the outer rim that this top part has to fit inside, the user just outlines that using the same kind of intelligent scissors that I showed you earlier. And so this red curve is the curve that the user has outlined. Okay? And then we make two assumptions. First, we assume that rays that are traveling in the explosion direction from the near object to from the near direction to the far direction, or from the near object to the far object, intersect this curve at most twice. Right? And then we have a second assumption which says that at the second point of intersection, the top object is going to pass behind the bottom object. Right? So that allows us to break that rim curve into two pieces. The red part is going to be in behind, and the blue part is going to be in front. And now we can just extrude the blue part down, and that allows us to split this bitmap, to fragment it into two pieces. Okay? So now we have two pieces for the bitmap. We have this part that's in front and this part that's behind. And when we move that top part down, it'll properly fit inside the bottom part. Okay? There's a lot more detail in the paper about when these assumptions work and when they don't. But it turns out that they work in a lot of cases. Yes? Yes. Well, so we only have 2D information. And while it would be great to be able to do rotations, we don't know how to do rotations because that would be disoccluding parts of the object that you've never seen. So we can't do it with these 2D objects. At least I haven't figured out a way to do it. Yeah, it would be great to have that. Okay, so here's a video showing that fragmentation process. So again, we draw that top curve using our intelligent scissors, and then we segment that curve into two pieces based on the explosion direction, and then we extrude that bottom part, split it into two pieces. And now, when we push that top part down, it fits inside. Okay. So we're getting closer. Let me point out that this fragmentation does work for a number of cases. So if we have this sort of inner part, the push rod that's going inside of this outer dust boot, our fragmentation algorithm will work in that case. And in this case, you draw the curve around the rim of the hole, and the system will fragment that curve properly. It'll also work for non-planar cavities. So if you have this kind of cavity, you draw the outer rim curve, and then you draw the outer rim curve going down here like this, and then the fragmentation algorithm still works. You end up with this. And so, again, in the paper, we describe in more detail the cases under which this will work and which it won't. So once we've done this kind of fragmentation, we need to do a depth assignment. That is, for each one of these bitmaps, these fragments, we need to assign an order in the layering, right? That's what we call depth assignment. And the way it works is that we know the explosion direction tells us which part of the object is closer to the viewer, which part is further away. So that's an indication of the depth. And that starts to impose constraints on the different parts. So part A is closer to the viewer than part B, so part A should be on top of part B, right? That layer should be on top. The A layer should be on top of the B layer. We also find in the case of fragmentation that some parts fit inside other parts, right? And so when we have a case of a part fitting inside another part, we can take the two fragments and assign the correct layering relationships to them. So we have C fits inside D. We also have B fits inside D. And these impose a set of constraints on the layering relationships between the parts. And we can solve this constrained system to figure out an ordering for each one of the fragments. Okay? And once we do that, we get this kind of ordering which allows all of our parts to layer correctly with one another. One thing that I should tell you about in a bit more detail is how we figure out if one part fits inside another part. We do that by taking the closed boundary curve that we drew for fragmentation and figuring out the extent of that curve along a vector that's perpendicular to the explosion direction. And then we take the part that fits inside and similarly extrude its width, or figure out its width in the same vector. And if one extent fits inside the other extent, then we know that one object is fitting inside the other object. Okay. So in this case, these two parts are interlocking, and we can feed all of these constraints to our constraint-solving system to infer the layering relationships between parts. And that's pretty much the complete system. The one thing I want to point out here at this stage is that the author can fix incorrect interlocking relationships. There's an interface to do that. The author can say, well, the system didn't properly figure this out. We need to update the constraint in this case. And in fact, there's, in just about every stage of the system, the author can provide manual assistance that the system can then use to do the right thing. So in the fragmentation stage, the author can specify how to break the rim curve into two pieces if the system doesn't do it correctly. The author can directly fragment parts. And so there's always sort of this fallback to letting the author take over and do the full thing.
Thinking back to master cylinder operation, where you have an axis of explosion that goes this way and then another one that goes this way.
Yeah. Yeah. So we build a hierarchy of these explosion directions, and the user specifies that hierarchy when they're drawing out these stacks.
How does I assume this collapses correctly? How do you know? How does A know when to stop when it's overlapping D?
Okay. So you have to specify the maximum amount you're willing to allow an object to move. So you know the full. You know how far it can move in one direction, right? Because you're assuming that it's fully exploded to begin with, but you do need to specify where it stops.
When you have parts, for example, part B block the rear part of section of part C, I would assume that if the back of C, the part that I cannot see, was different, the artist would have increased the distance to show the asymmetry.
Yes.
So because he or she didn't do it, I can assume that there is no need to draw C as going along the line of B. I don't see a reason why not to complete C along the arc that is invisible. And this way, I can assume sections that are invisible and then provide for actually even rotation, because I assume that parts that are not visible are identical to parts that are visible along symmetry.
Yeah, so that's a great idea, and it's definitely something that we'd love to explore further. So I think what you were saying is that when we in assuming that this is in a fully exploded state, when we segment the objects initially, there might be holes in some of the occluded objects. So here, there's a hole sort of in the C object, or here. And we could possibly fill that in by knowing that there's symmetry in this object, right? And so we could have a complete bitmap. The hard part then would be to do rotation in 3D, because you still don't have 3D information.
But even the symmetry is hard without 3D, because when I look at that, or you look at it, you see a bunch of feet which are geometrically symmetrical. And if you actually look at the pixels, there's white ones on one side, black ones on the other, and all the lighting effects.
That's right. And there's perspective effects as well, right? So it's not exactly clear how to fill that in, taking account for perspective. But perhaps what you could do is let the author specify the symmetry and specify the perspective. And you can give more and more tools to the author to try and do that whole filling. It's a great idea, and I think it's worth exploring the kinds of tools that you might provide. Okay, the final stage is a very simple one. We add labels, and labels are really, really useful for these kinds of drawings. So we just specify the label for the part, specify its anchor, and the position for the label. And we do that for all the parts. We can also provide guidelines. And one thing that I want you to notice, I'll play that again, is when I put in the guideline, it automatically figures out how to occlude that guideline properly. Okay? It figures out that this part is in front of this part, and so we should occlude it in the proper way.
One of the uses is, of course, understanding the mechanism that's been exploded. The other use is getting access to it. Do you treat fasteners in any different way? And I mean, sometimes they're ablated. You see the bolt, but you don't see the nut. It might be a hidden non-captive fastener, which is horrible.
Right. We don't treat them in any special way, and it would be neat to think about how we could. We basically are just taking the parts that you see in the original diagram and using those directly. So let me show you a little bit more on the viewing side. So that was the authoring. Now we have a complete interactive diagram. And as before, you can press a button. The whole thing expands and collapses. The labels disappear as necessary. You can actually you can also go in and directly manipulate this thing, pull it apart, see the different spatial relationships between the parts, and interactively filter the diagram to look at just the things you're interested in.
You were talking about having, I have to tell it how far down it can go or whatever. Have you thought about having, if you had it provide, you have it provide the exploded, if they provided exploded and unexploded, and then just let the algorithm derive, that's what it's supposed to look like. Therefore, what can I assume about how it goes together, or get some information from that?
We haven't thought about that. It would be great if it could do that. It sounds like a tough problem to, you sort of have to figure out how to the mental reassembly that you do, the system would have to kind of figure out, it sounds like.
Yeah. Well, I guess at least for things like the lid only goes this far, I can see, because there is the limit, so at least they don't have to specify. Yeah,
that's true. But, Here's a more complicated object, a lot more parts. One of the things that can be difficult with these kinds of objects to see where small parts are located, like that speaker. So we also have this kind of search interface. You can find the speaker by name and then just explode the parts as necessary to see that one-off part. Okay. All right, so that's pretty much the complete system. There's a few little things that we could add on to this. One of the things we've thought a little bit about are adding in arbitrary explosion directions. So if you look at this original master cylinder, there's this explosion axis that kind of moves in multiple directions. It kind of folds up the exploded view. And that's really nice for a static diagram, especially where you want to conserve a little bit of space and use up some of the white space. It's not so clear if this would be a good thing to do in the interactive setting. Here's another thing. So in very complicated objects, this is a piece from the inside of an IBM copier. With very complex objects and lots of parts, it can be difficult to see all of the little small fasteners and other parts in there. And so one of the things that might be nice is to just move the mouse over parts that you're interested in and maybe zoom them up in a regular zoom, or maybe we apply this idea of semantic zooming where we abstract the other parts in a variety of ways and really emphasize the part that you're interested in. And so I think that might be useful with really complicated examples.
But the system around me can effectively pull out the part, bring it closer to me to see more detail. That kind of idea. So you don't just go up and down. I can actually zoom in on an individual component. Yeah. As long as I've given you that boundary plot for your.
Yeah. So it would be nice to bring it closer to you. The things that we can't change are we can't change the occlusions, but we also can't change the resolution of the original image.
Yeah, so you have control of the content.
Yeah, right, yeah.
If you look in complicated objects to the semantics of the automatic detection of what is the innermost between the parts, so the system can infer it, and then ask the user only to distinguish when it reaches ambiguities?
We haven't done that in this 2D case. We've done some other work on 3D exploded view diagrams, so where the input is 3D models. And in that situation, we've done a lot more geometric analysis, including these kinds of containment and blocking analyses. Okay. All right. So I should see how we're doing for time. Okay. So the last thing I'd like to talk about is a recent project on creating cutaway illustrations. So far what we've talked a lot about is creating exploded views where you separate the parts of an object. Cutaways are an alternative way to look inside complex 3D structures. And what's nice about cutaways is that they leave the parts in place. So you don't have to mentally reassemble. Okay? But the trade-off, the price you pay for that, is that you're removing something from the object. You're removing a piece of the outer occluding surfaces. And so the challenge is to design cutaways that do show you the internal object, but also give you some sense of what you've removed. So here are some examples. This is a 3D model, and if we render it without cutaways, of course, all you see is the skin. What you'd like is to be able to create these kinds of illustrations where you can see the layering relationships between the muscles in the neck, for example. Okay. So here are the design principles. We looked at quite a few medical illustrations. We also talked to medical illustrators, had medical students draw examples for us. And from looking at all of that, we figured out a few things. One is that it's important for cuts to respect the geometry of the occluding parts. All right? We want to reveal the layering relationships between the occluding parts and the parts you're trying to expose. And so the reason you want to respect the geometry is that this can provide a way for viewers to mentally reconstruct the missing geometry. I'll explain this in more detail in a few minutes. But the idea is shown here, for example. So here we have this kind of tube. I think it's a vein in the neck, and a piece of that vein is missing. Okay, but you can mentally reconstruct that missing piece, and that's the kind of and that's because it's been cut in a particular way that helps you to mentally reconstruct it. The other thing is that we want to make interactive diagrams. And as part of this interactivity, I think it's very important for the interaction to be constrained. And we saw an example of this kind of constrained interaction earlier with that Voxelman 3D that I showed you, where the user was just constrained to moving a cutting plane through the object. That was pretty highly constrained. Here's another example from Voxelman. This is a great system, by the way. So here, this is a QuickTime VR viewer. And if I move my mouse left and right, if I can get the focus. OK, if I move the mouse left and right, I just rotate the object. And this is pretty standard QuickTime VR. But even this kind of direct manipulation and 3D motion parallax allows you to better understand the 3D structure of the object. Okay, so I rotate it in one direction. Now, if I move the mouse in the vertical direction, right, I start removing layers. And so I can just go through the object like this. I can rotate it. I can remove layers. And these kinds of constraints help me to understand the relationships between the parts. Now, this is a very simplified notion of layering, right? Large organs are just completely removed. Once I've removed a layer, it can be difficult to mentally reconstruct that layer. And so that's a little bit of a drawback with this system. Of course, the fact that you have interactivity allows you to bring it back right away if you want to see it. But sometimes you want to see the layers all together in a single visualization. So what I'll show you next is an attempt to show this kind of layering relationships in a single visualization. Let's see if I can bring that up. Okay, so this is work done at the University of Toronto by McGuffin and his colleagues.
Volumetric data.
And
pop up a radial menu and select the hinge.
I'm just going to turn off the volume there. So this is the volumetric data, and they have a very simple layering model. So they have the skin, and they have the next set of voxels inside is the next layer, and the next layer, and the next layer. So it's almost like a set of pages in a book, or onion skins, right? There's one layer, and then the next layer, and the next layer. There's no interpenetration between the layers. And then they have these kinds of interaction techniques. This is called the hinge spreader. You just push this hinge into the object and pull apart the angle of the hinge, and you can start to see inside of this object. Okay? And here the user has really full control, right? As a user, I have to go in and really place that thing very carefully in order to see the parts of interest. And the hinge spreader doesn't know anything about the geometry of the object, and so it doesn't respect anything about the geometry. And I, as an author, have to go in and very carefully choose where I want to spread this thing apart. On the other hand, this is a really nice sort of fluid interaction. It helps me understand the layering relationships between the parts, and it's a very nice interactive system in a number of respects. Okay, here's one more thing that you can do with this system. You can just sort of pull it apart. They took a lot of inspiration from working with books, right? And so there are a number of ways in which you can sort of interact with the pages in a book, and this thing provides a number of the similar kinds of interactions. So here I'm just putting the layers back together and so on. Okay. So that's that system. And so what I want is, I think, something in between these two systems. So the volumetric browsing system, well, it has these nice interactions, but it's a little under-constrained. I have to very carefully choose what I'm doing to create nice, effective illustrations. With the VoxelMan 3D, I'm really highly constrained. I can rotate in one direction, I can pull off complete layers in the other direction, and I can't do anything else. And so, so what I want to design is better interactions that allow me a little more control, but not too much control. So how should we cut away objects? Well, in order to figure this out, we looked at a wide variety of cutaways, and we identified some of the cutting conventions that are used. And a lot of these are based on the geometry of the part being cut. Here are 4 different conventions. When we have these kinds of rectangular prisms, rectangular solids, object-aligned box cuts are commonly used, right? When we cut an object like this, we can mentally very easily reconstruct what the walls of this rectangular object were supposed to be like. Now, in a lot of cases, particularly in anatomy, we have an outer shell that's covering internal organs. And when we have these kinds of free-form shells, we sometimes want to create what we call window cuts. We want to just cut a little window into the outer surface, but we want to retain enough of the outer surface so that, again, we can mentally reconstruct the shape of that outer surface. When we have these kinds of tubular objects, one thing we might want to do is create these kinds of wedge cuts. Just remove an angular wedge out of the tube. And again, there's enough context that is preserved that allows you to mentally reconstruct it. And finally, for some kinds of tubes, we want to make a cut that's just transverse to the primary axis of the tube. We cut all the way through it, and if the tube is thin enough, we can, again, mentally figure out how that tube extends. So these are cutting conventions that we commonly find in medical illustrations, in textbooks, and so on. Here's one more convention. This is the insetting convention. When we have objects like this with multiple layers, we often will cut things so that layers are partially remaining. Okay? So the outermost skin layer is cut back the most. The next layer of muscles is cut back a little bit less. The next layer a little bit less still, and so on. And so we get this kind of insetting as we move down through the layers, and so we can still see all the layers above, as well as we can see the internal vein or whatever structure you're interested in. And so this kind of insetting is very, very important, again, for understanding the relationships between that internal part that you wanted to see and the parts that are occluding it. So our system is designed around these cutting conventions, and I'll just give you a flavor for how they work in the system. So here's the box cut, and the way we set this up is that we have a simple parameter space that controls the cut, and that parameter space gets mapped onto a cutting volume in model space. So here's the various spaces. The important thing to remember is that the parameter space is always treated as sort of this rectangle in either 1, 2, or 3 dimensions. And that gets mapped into various geometries in the model space. Okay, so for box cuts, you map a box to a box. That's very simple. For these kinds of tubular objects, we map a box to this kind of wedge. And for these kinds of tubes where you're making a transverse cut, we map an extent in one dimension to an extent along the curve along the curve of the tube. So there's a mapping from this u-axis to the primary axis of the tube, and then any extent along this u-axis gets mapped into a cutting volume in the model space. And then finally, for windows, there are 2 kinds of windows. In one case, it's a one-dimensional family of curves we start by asking the user to draw the outermost curve, and then we compute a family that sort of pulls in the curve to its center, right? So we have a one-parameter family that indicates sort of the radius of this window. The other way to do this is the user draws 2 boundary curves, and we complete that into a 2-dimensional rectangular region on the surface, and then any rectangle that's drawn within parameter space gets mapped into a model space rectangle. Okay, so the basic idea here is that this mapping provides a convenient way for the user to specify a particular cut in this simple parameter space, and that gets mapped into a more complicated geometry that you're going to remove in model space. So here's how the system works. We start with an object, and then there is an authoring interface. The user has to do some work. In particular, the user is specifying the type of each object, what type of cut should be done on each object. And then the system, so the user specifies whether an object is a tube, whether a wedge cut should be performed, whether an object-aligned box cut, and so on. And the system then computes the geometric scaffolding, the mappings between parameter space and the model space, as I showed you earlier. The other thing that users might provide is a set of viewpoints on the objects. These are essentially good views of the objects. And then finally, there's a viewing interface. And this is where a viewer can then go in and interactively look at the parts that they're most interested in. So this is the rigging system. It's very, very simple. It's very simple. I'll just play this video to show it working.
We now demonstrate how a user creates an interactive cutaway illustration
You
using
hear
the
that?
authoring interface. First, the author categorizes each part as one of the 4 geometric types shown on the right. Here, the user selects the tire and rim, and then hits a shortcut key to label them as radially symmetric parts. In this way, the user quickly categorizes every part in the model. Based on this categorization, the system automatically constructs the mappings for each part. Here, the mappings are visualized in pink. For this model, the entire process takes less than a minute. In a few cases, it may be difficult for the system to compute the desired mapping without higher-level knowledge. For these 3 parts, it is not obvious where to place the axis for creating wedge cuts. In these cases, we have a UI to let the user override the automatically computed mappings. After selecting the parts, he orients them so that the viewing direction aligns roughly with the desired axis, and then clicks where the axis should be positioned. The system then constructs the new mappings by snapping the axis to one of the model's canonical axes and snapping the clicked point to the model's centroid. In practice, this type of manual editing is necessary for just a small fraction of parts.
Okay, so the main work involved here is just classifying the parts, whether they're tubes, object-aligned, and so on, and the system is constructing the mapping, except in a few cases where it does the wrong thing, and then the user can go in and fluidly add more annotation to get the right result. Okay, so the other thing that the user needs to provide are some good viewpoints. So here's an example. The user just orients the object into a particular view. That's a good view. And then the system will go and compute an occlusion graph. And the occlusion graph essentially encodes the layering between the different parts for that viewpoint. Okay? So let me show you how this works. We start with the complete object. And when we render that complete object from the given viewpoint, we find that the skin is the frontmost object that you see. That provides the topmost layer in this occlusion graph. And we remove the skin, and we find the next set of objects. We find all these muscles, and they provide the next layer in this occlusion graph. Okay? We remove these muscles, find the next layer, and so on until we build up the entire set of layers.
Do you have something like this?
Mm-hmm. Yeah, so what we're doing is figuring out, we don't break that into 2 pieces. What we do is figure out which layer contains most of the object. Okay. Typically, there's one layer in which that mostly resides. So there's a threshold essentially in the system. Okay, and then we're going to use this occlusion graph to construct the insets, right? We're going to cut away the outermost layer the most, the next outer layer less, and so on. And then we also are going to use this graph structure to help pick good views of the object. There's a portion of the system which can automatically pick good views when a user is interacting with the object. So let me show you this video that demonstrates the system.
Once the model has been authored, it can be explored using our viewing interface. To expose a particular target part, the user just selects it from a list. The system automatically chooses the best saved viewpoint and creates a labeled cutaway illustration that exposes the target. The user can also select multiple target parts. For each set of targets, the system chooses the most appropriate viewpoint. Now let's look at the authoring and viewing processes for a different model, this time an anatomical example. For membranes such as skin, the system automatically constructs a mapping for creating window cuts that expose occluded parts. Here, the author overrides the mapping to create a window of a different shape. First, he sketches two lines to indicate the extent of the window, and then the system automatically computes a boundary that follows silhouettes and geodesics along the surface. When the model is viewed, the window cut resizes itself automatically to expose the parts of interest. We now show some other features of our viewing interface. Here, the viewer clicks to expand each layer of the thorax. To better reveal the cross-sectional surfaces of the structures that have been cut back, we allow the viewer to bevel cuts towards the current viewpoint, as shown here. Here, the viewer explores another anatomical model. Our system supports simple shading techniques that can improve the quality of an illustration. Here, the user enables edge shadows that emphasize depth discontinuities, and edge shading that suggests the relative orientations of cut surfaces. As part of the authoring process, parts can be organized into logical groups. The viewer can then expose each group in order with a single click, as shown here. In addition to automatically exposing parts, the viewer can directly manipulate the cutting parameters of individual cuts. Here, the user draws a stroke to open up a cut, and then interactively modifies its size and position. We also support constraint manipulation, where the system enforces inset constraints in real time. Here, notice how insets are maintained between the various housings of the turbine model. Finally, we show that our system can generate effective cutaways of an engine model that contains well over 100 individual parts.
So you're seeing the system in real time. The pauses are because it's computing things.
In this video, we have demonstrated our system for creating and viewing interactive cutaway illustrations of complex models. Thank you for watching.
So that's the basic system, and and we spent a lot of time building the cutaway system. One of the things that we've recently started looking at is combining cutaways and exploded views, right? So rather than just cutting and removing parts, we're now going to cut and then separate parts. So combining the two interests. Here's a basic idea of what we are hoping to be able to do. This was sort of done up by hand, but basically cut the part automatically, figure out what the places that we should cut it, and then pull it apart. And so the two techniques together, I think, could be very, very powerful. Here, I'll show you one last little example of that. Here we're sort of taking account for symmetries, and all the parts are moving together. We can also interact with individual parts. And I think there's more that can be done here to really figure out the right set of interactions for doing both cutting and exploding. Oh. Yeah, so that's something that we noticed in a lot of examples as well. So when you insert a cutting plane into an object, the region that you've cut, the portion of that plane against the surface that you've cut is normally colored in a very distinct color. It sort of highlights the fact that you've made a cut there, and you can see the outline of the sliced part. So again, it helps you sort of mentally reconstruct what's happening. Yeah. Yeah.
Color pattern on the outside. You cut it, it would not show that. It would just show this.
Yeah. So that would be it. Going forward, there are other types of models. I would like to go back to these kinds of mathematical models and really figure out how to automatically expose important features, right? The internal self-intersections and so on. These examples are really inspiring. I already talked about Cassidy's example. George Francis is a mathematician who wrote a book called A Topological Picture Book, and it's full of these kinds of illustrations. If you're interested in this kind of stuff, I really strongly recommend that book. And then finally, we did these image-based exploded view diagrams, and it turns out that there are a lot of exploded view diagrams, static exploded view diagrams in the world. I think there are even more static cutaways. And so one of the things that we've been thinking a little bit about is whether or not you could take this kind of cutaway illustration and turn it into an interactive cutaway. That is, fill in the holes and then allow a person to cut where they want. All right? So this would get at some of that hole filling that we were talking about. You'd have to reconstruct the outer surface, and then if you could do that, then you have a layered drawing, and a user could go in and sort of reveal the parts that they're most interested in. And one last thing I should point out here. So, we did this work on exploded views and cutaways, and at the very beginning of the talk, I pointed out, well, it's a three-step process. We identify the design principles, we instantiate the design principles, and then we evaluate the resulting visualizations. And one of the things I didn't talk about in this talk is evaluation. And that's because in the projects that I showed you, we haven't done the evaluation. All right? Evaluation is hard. It's not exactly clear how to do it. There was a project that we worked on a while back, again, as I was finishing at Stanford. It was a project on creating assembly instructions for 3D objects. In that case, we were able to work with Barbara Tversky and some of her colleagues in psychology to design an evaluation study. And there, what we evaluated was 3 sets of instructions. These were the instructions that came with this TV stand model. These were instructions that users in our studies created. These were sort of the most highly rated instructions. We had users rate different people's instructions, and these were the most highly rated here. And then these were computer-generated instructions. And we went through the step of having a user study. Users came in, used the 3 different sets of instructions, and we found that our instructions were fairly good. They were better than the other 2. But it's not all, so this was a case where we could do this kind of study. And that was good, but it's not always clear how to design the right kind of study to really evaluate the effectiveness of your visualization. So in the case of the cutaways, how should we evaluate whether users are able to see the right information in the visualizations that we give them? This is not clear to me, and it's something that I think I'd like to work on, and I'd like your help. So I encourage you to think about this problem. Just to finish up here, we have a 3-step approach. We identify the design principles, and there are 2 kinds of design principles in the work that I've shown. One is on the visual design. How can we create these images, and how can we create them in a way that communicate information? The other is on interaction design. So we want to design interactions that, again, help convey the information. Next is instantiate these design principles. And here we want to create, we often create these semi-automated authoring tools and let the user provide input where necessary. And finally, we need help in evaluating the resulting visualizations. So with that, I'll end. Thank you very much. And yeah, questions?
Yeah, it was interesting. If you compare your TV stand example with the instruction with the museum layout. In the museum, you said that having everything visible together in one structure was better. But in the TV stand, that seems not to have been true, because the original instructions were that principle. Is that just because there's steps, I mean, there's sequence involved?
Yeah, so there's 2 things, and that's actually something that came out in some of our early studies. So we compared a single exploded view diagram to these step-by-step instructions, and what we found was that the single exploded view was just cluttered with too much information. It was hard for viewers to see the sequence of steps, even if they were numbered in sequence. It was hard for people to see, oh, I do this thing first, then I do this thing. It was hard for them to visualize what the thing would look like after each step.
And why would that not be true for the museum, where I really take one floor at a time?
Yeah, I don't know. I mean, this would be worth exploring, perhaps. But people want to see it in an integrated.
Yeah. One whole dimension here is you're trying to put it together, you're trying to go find it.
Yeah, that's a good point. Right. So if you were trying to find a particular part, maybe the exploded view would be better. Right. Yeah.
I'm not familiar with just where CAD is these days, but maybe you could say something about, because you seem to start from pictures rather than from, let's say, stored geometric shapes in CAD, and you then put the system together.
So, so that exploded, I showed 2 systems here, actually 3 systems. So the architecture one started from 3D geometry. The one in the middle was with images, and this last one on cutaways again had 3D geometry. So
thinking about the cutaways,
yeah.
Because, Boeing makes all their planes that way now.
Yeah. So there are very nice, complicated 3D models of the Boeing 747, and yeah, I think it would be great to try and apply some of these techniques to those models. Yes.
So, I mean, one of the purposes of an elaborate CAD model is to help understand dynamics, not just structure. And do you have any feeling about sort of what the conventional tools are probably within the CAD/CAM realm for illustrating that, particularly like say linkages.
Yeah. Well, there's a lot of work on simulating dynamics and physics, physical simulation. What's less clear to me is how to explain that to another person. And I don't know the work in this area, right? How to teach someone dynamics, especially when you have this interactive, maybe you have a physical simulator. How would you show them the dynamics? I think it would be a great problem to work on. Yes?
I fear that this evaluation may need some info that you don't quite have, but you talked about putting together instructions where presumably the instructions have to go in the right sequence where it's not manufacturable. And you talked about the goals of a user looking at an exploded diagram and evaluating. Well, if you're a mechanic and you're trying to get at maybe the speaker in the cell phone, and you already have a 3D model, and I've clicked on the 10 fasteners out of 100 that are sitting on my workbench, and maybe even told you there's another couple parts that are on the workbench, and I still tug on the device, and I can't get at the speaker. I think that I've gotten all the fasteners out, but it's not working yet. That seems like a fair goal to evaluate it. That's why I'm using the diagram.
Yeah, so are you suggesting that would be a way to possibly do the evaluation?
Yes,
or
it might be hard for you to figure out. If you know that there's 90 fasteners and there's exactly one that needs to be removed, it might be difficult to figure out how to help the mechanic.
Right. Yeah. So I don't see exactly how you would use that for evaluation, but I could imagine that being a task that you could help with through.
Evaluating on a task to see, you give a mechanic, okay, here's the diagram, go find the speaker, and you see if it's effective in helping him.
Yeah, yeah, right. Yeah, I think that would be a good thing to try and do. In the back.
Do you know how, if they're generating these exploded and cutaway views today, like if you're working with CAD programs, are they just doing it by hand, or are they?
Yeah, it's a very manual process. So there are a few tools in there, but they're not very sophisticated, and so you end up spending quite a lot of time just manipulating the parts, manually dragging them one by one apart from each other, rotating them into position, and so on.
Those users on whether or not a system like yours would be more helpful or less helpful?
We've talked a little bit to them. We should do more, certainly. So yes and no. Yeah.
Just in terms of the evaluation, it seems like it's kind of somewhat tailor-made for online, where you say, come in here and we show you, we're going to show you these things and ask you to find something out by using this interactive or static, and then you just randomly give different people different models or different views and see what their success rate is. And, and then you can have people from all over. You can have Terry assign all his students to do this.
Yeah. Well, the internet certainly enables new forms of testing and evaluation, and I think you could probably get some valuable information that way.
Are you more worried about static, like pictures of cutaways, or interactive things?
A little bit of both. I mean, we're really interested in both the visual design and the interaction design. The two things go together in a lot of cases. So.
How well would it work if I did this photographically? I mean, I take this thing apart piece by. Is the system terribly sensitive to alignment?
It's sensitive to a few things, but alignment, yeah. I mean, you really have to give it an exploded view, right? If you give it an exploded view where things are lined up, then it's much easier. There's also a little assumption that the objects are in parallel projection, not perspective projection. And if you have, so you have to do a little trick with your camera to get it to do a parallel projection.
Okay. Thank you.
Yeah, thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.